Okay, so welcome everybody. Thank you for listening to this tutorial. Here we're going to be exploring the properties of metals. Now in our periodic table right here, there are a few, groups of metals that we're going to be exploring. So metals are essentially, if you need the definition of a metal, their property, the property of a metal is that metals lose electrons. So they're elements that are capable of losing electrons. Now we know from our study of the periodic table that elements that lose electrons tend to be on the left-hand side of the periodic table. So if you look at this group here, lithium, sodium, potassium, and all the way down the group, these are very, very reactive metals. Now what makes them metals is that they only have one electron in their valence shell. So if you drew out lithium, lithium would have two electron shells, and in the final electron shell it would only contain one electron. So that electron can be released, can be given off very easily. Okay, so these are group 1 metals. So we know that metals lose electrons, and the specific name for this particular group here is the alkali metal. Okay, now this group here, beryllium, magnesium, calcium, so forth, this is known as the group 2 metals. Because remember that group, I may as well stay consistent and write the Roman numerals, group 2 metals. So the group 2 metals are known as the alkaline earth metals. And so these this group here can actually release 2 electrons. Okay, so magnesium, it's in the second position along the period. So what that means is that magnesium has 2 electrons to give away from its valence shell. Now that makes it slightly less reactive than the group 1 metals, but they're still very, very reactive. Okay, so these are the alkaline earth metals down here. Now when we get to this particular section here, from there to zinc, these are called the transition metals. Okay, now you don't have to really know too much about the transition metals. They do behave slightly differently than the group 1 and group 2. They have magnetic properties, they tend to have different oxidation states. What that means is, like, if you pick out maybe iron can be in its oxidation state of 2+, or it can be just Fe+, or it could be Fe3+. And that's just, these are all different oxidation states, so they can behave differently. Notice how it's still a positive charge, meaning that iron has still released electrons, which gives it its metallic characteristic. But yeah, they behave a little bit differently than the group 1 and group 2 metals. They're a lot more complicated. Okay, now down here we have aluminium, and so there's this procession downwards where we know that it kind of goes like this. And so these are still metals here, and these start becoming, on the right hand side, the non-metals. Okay, so Aluminium is still considered a metal, and that's because it still has the capacity of releasing 3 electrons. And so we know that the main definition of a metal, what distinguishes a metal, is that a metal can lose electrons. So I wanted to explore the properties of metals today. Now, the properties of metals, listed 4 main ones, the ones that VCAR asks you to understand thoroughly and be able to explain. And the first property is that metals tend to be strong and they tend to have high boiling points. Okay, we'll explore each of these points as we progress through the tutorial. So basically what that means is that they're pretty strong, meaning that you can't really twist and bend them very easily. They have high boiling points, so you can't really melt them at a low temperature. You need a significantly high temperature. Now, the exception for that, there's always exception to these particular rules. The exception is mercury. Now, mercury in the periodic table, Hg right there. Mercury, as you know, is in maybe you know, is actually a liquid. It's been used in thermometers, so to test people's temperature. It's highly toxic, and it's actually in a liquid phase. So that's the exception. There's always exception to these chemistry rules. Now, metals are lustrous. This basically means that they reflect light and they look shiny. So lustrous means shiny, and we know that metals tend to, if you look at an aluminium can, it tends to be able to reflect light. And there's a specific reason that they can do this. It's not just there is a chemistry behind that. There is chemistry behind that. So metals conduct electricity and heat. So as we know, copper is right here. It tends to be one of the main uses for electrical wiring, and that's again due to the properties of metals. Copper has been seen to be one of the most preferred metals used in electrical wiring because it's relatively cheap and it's easy to turn into a wire. So manufacturers make a lot of electrical appliances using copper. Now, heat, if you ever have tried to cook with a metal spoon, you will find that that spoon gets extremely hot, and there is a reason why it does, and we will explore this in a moment. But metals are able to conduct electricity and heat. Now, these 2 words, metals are ductile and malleable. Ductile is a very important concept. You have to know this for your exams and tests. It is essentially the ability of a substance to be turned into a wire. So not all substances in chemistry can be turned into a wire. If you try to take a substance such as salt, just your normal table salt, obviously you can't really extend that into a wire, and that's because it is a different type of chemical than metal. So metals have this very interesting ability of being able to be turned into a wire, and there's a reason for that. Now, malleable means that metals can be shaped. So if you've ever tried to maybe use a spoon, a metallic spoon, to dig out ice cream out of a container, you'll maybe run into a problem where the spoon sort of starts to bend and starts to the metal starts being shaped into a different kind of configuration. And this is the malleability of the metal. So basically we can make different types of metals. You know, in the industry we need to make structures. We can kind of transform metals into different kind of configurations to use in you know, design, etc. So they have the ability of doing this. Now if you take again something like salt and ionic substances, which we'll look at in future tutorials, you can't actually shape ionic substances into anything you want, because there's a limitation on them, and this can be explained through chemistry. Okay, now what I've actually presented here is something that you really need to understand. This is a two-dimensional picture, and it's actually something that you can refer to as the metallic bonding lattice. Now a lattice is just a collection of ions, well, it's just a large collection of atoms and elements, usually in its ionic form, and it's three-dimensional. So actually this is just the first layer of what's going on in the material. So what you have, let's choose something like magnesium, for example. Okay. Now magnesium, as we know, has the capacity. Well, magnesium contains 2 valence electrons, and therefore what it will do, if we draw it out, magnesium, it's in period number 3. So it has 3 electron shells. In this first one, we're just using Bohr's model. There's 2 electrons. In the second one, there's 8 electrons. And in the final valence shell, there's actually 2 electrons. So those electrons there, they can be lost. Okay, so what ends up happening is that the magnesium, once those 2 electrons are lost, the magnesium actually becomes Mg2+. Now this is known as a cation. A cation is a positive ion. Okay, so it's got a positive charge. Now have a look at how this lattice is formed. So metals always will lose electrons. That's the definition of a metal. A metal will always lose electrons. Okay, so these positively charged ions here, they're known as cations. And they, in this case, they're the metal that lost electrons. So you can see a whole stack of, you know, there's an arrangement going on here with all of these positive ions, which are cations. Okay, so they're all sort of arranged in this sort of way. And here, these electrons, they're actually delocalized electrons. Now what I mean by delocalized electrons, so delocalized electrons are electrons that are no longer part of the original element. They're sort of free to move in between the cations. So these electrons are not bound anymore to the original atom. They're free to roam. Okay, so the importance of this particular, so going back to this, all of these, say in a magnesium substance, you would actually have 2 electrons. If I were to draw 2 electrons, you have billions and billions and billions of cations. Remember, if you like look at it through, you know, an electron microscope or something, you have billions of these. arrangements, and each one of these positive cations release 2 electrons, and it produces this huge amount of delocalized electrons within this structure. So these might be magnesium 2+, and within that structure you have all these delocalized electrons roaming around. Now the significance of this, in terms of our first point, metals are strong and have high boiling points. The reason why they are very strong is because, as you can see, there's this electrostatic charge between the positive cation and the negative electrons. So if you look at say the difference between, you may say, okay, well, there's a cation, there's a positive charge here, and there's also a positive charge here. You may ask, won't they repel? Positive and positive, you know, they will want to repel against each other, but it actually doesn't repel. And the reason why not is because you have all of these delocalized electrons that are cushioning the 2 polarities of charge, you know, so they're all contained within this structure. And that means that not only are metals strong, so they're very hard because of this, because they're, you know, they're very stable. They can't really be pushed apart together very easily. They also are very dense. Dense meaning that, you know, a metal, for the amount of metal that you have, it's quite heavy. You can see it's got a very compact nature. If you have a positive charge here and a positive charge there, so a positive ion up here, in other words a cation up here, and another cation down here, which are both magnesium, they can actually move very, very close together. And the reason for that is because the electrons are so tiny that they will be able to fit in between those gaps between the positive and the positive. They will be able to squeeze their way through those little gaps, and electrons will prevent the positive and positive from being able to ever meet. So this lattice can actually be very compact. Now, high boiling points. The reason why metals have such high boiling points is if you actually want to tear this structure apart, there is a very, very stable, these metallic structures are extremely stable. I mean, you've got the positive charge here and the negative delocalized electrons that are roaming around, and then another layer of positive and then another layer of negative and so forth. So it's actually very difficult to turn this into a liquid state. So it will take tremendous amount of energy to tear up the position of these ions and their electrons into a liquid state. It requires a huge amount of energy, and usually you'll find that metals tend to melt only when you reach 1,000 degrees. So they go from solid to liquid at about 1,000 degrees. That's the amount of energy that you need to provide for that particular lattice structure to break apart. So for the positive and the negative charges to sort of move away from each other, you need about 1,000 degrees. So not for every metal, because obviously, as I said earlier, mercury tends to be a metal which can actually be liquid at room temperature, but the majority of them will be incredibly strong and will have high melting, high boiling and melting points. Okay, so now to our next point. Metals tend to be lustrous. Now, I'll just make a bit of, I won't erase the electrons, but so this idea of lustrous that just means they're capable of reflecting light. So if you imagine a light wave sort of coming in to hitting a metallic surface, so this is my light here, what happens is that electrons tend to reflect light. We know that from physics, that and you don't really need to concern yourself too much of this in chemistry, but when a photon of light hits an electron will reflect that light. Okay, so the light will be reflected, and this is what will make the actual metal shiny. Okay, so it's because of the delocalized electrons. So the next point, metals tend to conduct electricity and heat. Okay, so again, every single one of your explanations need to correspond to the metallic bonding lattice. And, you know, it's usually due to the delocalized electrons. So when you're explaining in a test why, you know, you have metals conducting electricity and heat, you need to speak about the delocalized electrons. It's very important. So metals conduct electricity, and that's because they have delocalized electrons. Okay, so these electrons here, they are capable of just moving through a structure. So metals conduct electricity since the delocalized electrons can move, and heat is exactly the same. Okay, so what happens is if you have say maybe you have a bit of heat on this side of your structure, so there's hot temperature occurring, so heat. What will happen is that these delocalized electrons, they will really gain a lot of energy, and they will start rebounding against each other. They will start moving very rapidly with a lot of energy, and they will rebound rapidly. And that means basically that, you know, if you have, say, a cooler temperature down here, you know, you have this diffusion of heat along the structure of the metal, because eventually it's inevitable that these electrons that are moving very rapidly will influence the electrons on this side of the metal, and so you will have, you know, this heat being transferred across. So eventually this part of your metallic structure, say maybe a spoon, will get warmer because there's more energy between each of the electrons, and then this part will get slightly warmer, and that will inevitably heat up the other part of the spoon or whatever metallic structure you're using to warm up. And so this is why it's never a good idea to heat with a metal spoon, because that's just going to the delocalized electrons within your metallic structure are going to move and influence delocalized electrons down the metal lattice. So eventually the heat will be transferred across the metallic structure due to these delocalized electrons. Okay, so let's have a look at the final point. Metals are ductile, which we said earlier that they are capable of being turned into wire, and they are malleable as well. Now, let's have a look at this. So, they're ductile because, as we know, okay, the special thing about a metal is that you can have, say, your cations here, all arranged nicely. And I'll explain malleability and ductility in one step. Okay, so let's say you had a certain force. So a certain force hit your particular metal. And so because there are a whole stack of delocalized electrons in the structure here, those are my little delocalized electrons, means basically that the layer of metal, and these are not very consistent, I'm sorry about that, I can't really draw circles very well, but if you add a particular force, oops, I haven't updated my computer for a while, it's angry at me. So if you have a particular force that's applied to your particular metal, that metal will slide, or can slide across like this. So you have a block here, your particular metal, and it's usually three-dimensional, so don't forget that these lattices that we're looking at are three-dimensional, and this is where my capacity as an artist diminishes. So you add a force, you might beat this particular metal into that shape, and that won't tear up the structure. The metal will just simply bend. And again, that's because whether it's in this shape here, this three-dimensional shape, or that three-dimensional shape there, essentially every single cation is still stable because it's still covered with these delocalized electrons. And this is what gives it its malleability. And also this is what allows the wire, a metallic wire, to be formed. Okay, now if you looked at ionic bonding, which that's actually the next chapter in our tutorial, but ionic bonding is a lot different than metallic bonding, and the reason why is because within ionic bonding you have a positive ion followed by a negative one followed by a negative one. So remember that positives and negatives attract, so you have this kind of arrangement, and these are ions. So this is in ionic bonding. So you still have a three-dimensional shape and everything's good and stable, and then you try to hit it with a particular force. So here's my force, and then what happens is that this happens. So let's imagine that you hit that with a particular force, that ionic. This is an ionic. I'm just comparing ionic with metallic. Metallic has the delocalized electrons, ionic actually doesn't. So what will happen is that the positive, negative, positive ions will sort of, if you imagine this layer maybe staying as it is, and then this layer down here actually sliding across. So negative, positive, negative. And perhaps this layer down here will slide across as well. So maybe that will be positive, negative, positive. So actually, if that happens in an ionic substance, okay, it will not be good news for that particular ionic substance, because what will happen is that the two negative charges and the two positive charges here will actually cause a tear in the not the metal but the actual structure. Again, positive and positive will repel. So this particular thing, this particular substance here will shatter or will break into smaller pieces. So you find stuff like materials such as salt crumbling, and the reason why it crumbles is because of these positive and positive charges repelling. There are no delocalized electrons in an ionic bonding model. However, the fact that this metallic bonding model has these particular electrons here, it causes the structure to be shielded away from just basically falling apart. Okay, the delocalized electrons slide together with the cations, and therefore the metal is able to be configured into different shapes and even put into a wire, which is ductility. Now that's very important in metallic bonding.